Hi students, today we are going to see the Cedric Theory, otherwise the EAN rule, otherwise it is also called 18 electron rule, and this is Vasudha. Now at the end of this video you are going to learn the Sidgwick theory, the EAN formula and calculation, relationship between stability and EAN, the examples and the limitations. So Sedgwick theory suggested that the metal ion will continue accepting electron pairs till the total number of electrons in the metal ion and those donated by ligands is equal to that of next higher noble gas. The total number of electrons is called EAN, effective atomic number. It is also called effective atomic number. So the rule of calculating the effective atomic number is called EAN rule. This EAN is related to stability of the complex. If EAN is equal to the atomic number of next higher noble gas, then the complex is said to be stable. If EAN is not equal to the next higher noble gas atomic number, then the complex is not stable. And this EAN rule can be better understood by taking the sum of the examples. Now here we can see the different noble gases or inert gases in the periodic table, and the helium, neon, argon, krypton, xenon and radium are the noble gases. So here now we will see what is meant by EAN and how to calculate the EAN number. So now EAN is the effective atomic number, and it can be calculated by using the formula Z minus ON plus 2 into Cn. So where ON, Z is the atomic number, ON is the oxidation number, plus 2 into coordination number. So this is the formula, and this we can call it as EAN rule. This is the formula we use to calculate the EAN number. So now we will see the calculation taking some examples. So if you see this complex, if you want to calculate EAN number, then we use this formula and then calculate EAN number. So now the rhodium, first of all we take the atomic number, so atomic number 45. So now this rhodium, if you calculate the oxidation state will come to plus 3. So 45 minus 3, because Z minus ON, so 45 minus 3 is equal to 42. Next plus 2 into coordination number, so plus 2 into coordination number is the number of ligand 6, so 6 into 2 12, so the total number is equal to 54. So now we can observe the 54 is the number of the atomic number is equal to the atomic number of xenon. So you can observe here the xenon, the same atomic number 54. That means the EAN is equal to the atomic number of an inert gas. That is why this complex is treated as stable complex, because its EAN number is equal to the atomic number of next higher inert gas. So now if you take this complex, so if you calculate the atomic number 27 for cobalt, the oxidation state 3 plus 2 into ligands, that is equal to 36. So 36 is equal to the atomic number of krypton. You can observe here the krypton 36. So this complex is also stable. So here are some more examples. So FeCN 6 times. So now for this Fe oxidation number 2. So in the calculation 26 minus 2 24 and 24 plus 12 36. So 36 is an atomic number of xenon. So this is also a stable complex. So it is equal to that of krypton, so it is a stable complex. So if you consider this complex, the total number it will come to 35, which is not a any inert gas atomic number 35. There is no 35, so krypton is 36. So now this 35 atomic number is not equal to the inert gas atomic number. That's why this complex is said to be not stable. So that is how we can calculate or we can compare the stability with EAN number. So if you see this table, so here also we got 36. So this is also a stable complex. So likewise you can calculate EAN for various complexes. So this EAN rule is otherwise called 18 electron rule, because if you consider the valence electrons in any complexes which obey EAN rule, then the valence number of electrons will be equal to 18. That's why this EAN is otherwise called 18 electron rule. So here are some of the examples for EAN calculations. So now all the first row complexes, they obey EAN rule because they obtained the inert gas configurations or inert gas atomic numbers. So these are all stable complexes, but many do not obey EAN rule. So these are the examples of complexes which do not obey EAN rule. You can see the atomic numbers which are not the inert gas atomic numbers. So there are some complexes which obey the EAN rule, they are stable, and other complexes which do not obey EAN rule, they are not stable. Still, there are few more limitations in this Sedgwick theory. Many complexes are stable, but they do not follow EAN rule. Thus, this particular theory does not predict the geometry of complexes, and this theory is not predicting the magnetic behavior of complexes. In next theory, we will see the rectifications of this Sedgwick theory. Thank you. Thanks for watching this video. If you like this video, please like, share and subscribe. Thank you.